in the night sky. Our telescopes detect flashes of blue light that flare up for just a few hours, shining brighter than a supernova, and then vanish. As if they were never there, they appear at random, only a few times each year. Scientists call them luminous fast blue optical transients, or LFBOTs. But the more we observe them, the more mysterious they become. Some explosions never fully fade, some repeat like a heartbeat, and one, detonated in the middle of nowhere, where no star should exist to die. Each event challenges a different law of physics, as if the universe is deliberately breaking the very rules it set for itself. And if that's true, then perhaps those blue flashes aren't just the death of a star, but the moment something entirely new is being born. In 2018, telescopes on Earth began to record a strange new phenomenon. Amidst images from sky surveys, a brilliant blue flash would suddenly erupt, blazing for a few hours before fading into nothing. When astronomers checked the data, they realized what they had seen was brighter than an entire supernova, yet it disappeared so quickly that nothing in known physics could explain it. These explosions were named luminous fast blue optical transients, or LFBOTs. They are a paradox too bright to be the ordinary death of a star, yet too fast to follow any known explosive mechanism. While a supernova takes months to peak and fade, an LFBOT does it in just a few days. They flare up like the universe's camera flash, rendering old theories obsolete. Even more incredible is their rarity. All of Earth's automated sky surveys, dozens of telescopes scanning the heavens every night, catch only a handful of these events each year. This means that, on a cosmic scale, these flashes are almost unique. Each appearance is a precious opportunity to look directly into the most extreme energy processes that nature can create. The first LFBOT was officially recorded on June 16, 2018. The Atlas telescope in Hawaii, designed to spot asteroids on a collision course with Earth, stumbled upon an incredibly bright explosion in the Hercules constellation, about 200 million light-years away. The event was designated AT2018 Cow, and the scientific community quickly gave it a shorter, memorable nickname, the Cow. At first, the Cow was classified as a Type Ib supernova, the kind of explosion that occurs when a massive star runs out of fuel. But the spectral data told a different story. Its light peaked after only a few days, shining more than 100 times brighter than a typical supernova. And its spectral lines were unlike any stellar explosion ever seen. As observatories around the world, from radio to X-ray telescopes, aimed their instruments at it, they discovered the strangest thing of all: the explosion didn't seem to be fading completely. Deep inside, an energy source was still glowing, ejecting material at 10% the speed of light. An explosion like this was unprecedented. It suggested that a powerful engine existed inside the Cow, perhaps a newborn black hole, or a rapidly spinning magnetar with an impossibly strong magnetic field. Both are objects born from the death of giant stars. If this was indeed one of them, the Cow had given humanity a front-row seat to the birth of a compact object, a moment where space, time, and energy become one. From that day on, the Cow became the symbol of a new era in astrophysics. The focus was no longer just on explosions lasting for months, but on ultra-short, ultra-powerful flashes that broke every mold. It showed that the universe could light up in an instant, not to destroy, but perhaps to create something new. After the Cow, astronomers began paying closer attention to this strange new class of explosions. They wondered if this wasn't an isolated incident. Was the universe hiding a pattern we hadn't yet seen? The answer came sooner than anyone expected. Just a few months later, at the end of 2018, a similar event appeared, nicknamed the Koala. 2 years after that, another explosion was named the Camel. All of them shared the same characteristics: intensely blue, incredibly fast, and so powerful they forced every old theory back to the drawing board. These playful nicknames gradually formed a cosmic zoo, with each new creature opening a door to yet another layer of mystery. But what truly captured scientists' attention wasn't just how they flared, but where they appeared. All three, the Cow, the Koala, and the Camel, occurred in the spiral arms of star-forming galaxies. This location was no coincidence. It's where massive stars are born and die in short lifespans of just a few million years. If LFBOTs were indeed a rare type of core collapse supernova, then finding them here made perfect sense. This clue gave the astronomical community the first feeling of a breakthrough, a common denominator. It seemed LFBOTs weren't a completely alien phenomenon, but an extreme variant of familiar stellar explosions where energy is focused into a tiny region, making the event flare up faster and far more violently. Several research teams proposed that the collapsing star's core had formed a compact object like a newborn magnetar or black hole, and that this engine was what powered the blue light in the first few days. Computer simulations showed that if this engine pumped out energy continuously over a short period, it could perfectly recreate the cow's light curve. With this hypothesis, LFBOTs finally had a plausible, if tentative, explanation. Still, no one dared to say the story was over. Scientists knew that whenever the universe reveals a rule, it's often just to prepare to break it the next time. But for a moment, a sense of confidence spread. They thought they were getting closer to the answer, just as astronomers thought they were beginning to understand LFBOTs. The universe threw them a curveball in 2022. While the Zwicky Transient Facility ZTF, an automated sky survey in California, was scanning the heavens, it registered an extremely powerful signal. At first, scientists thought it was just another familiar LFBOT. But then the data came in, and it left them stunned. The event was designated ATTT2SC and later nicknamed the Tasmanian Devil. The name was playful, but its behavior was anything but. Unlike previous LFBOTs that flashed once and then faded, the Tasmanian Devil refused to disappear. Just days after the initial explosion, telescopes saw it light up again just as powerfully as the first time. Then again, and again, in total. Over a period of 120 days, the Tasmanian Devil produced at least 14 distinct flares, each lasting only a few minutes but releasing the energy of hundreds of billions of suns. No one had ever seen anything like it. Normally, when a star explodes, that's the end. But here, the light was switching on and off, as if the universe were flicking a giant switch. Some scientists described it as a star that keeps dying and coming back to life. It sounds like a metaphor, but it was the closest description of what the observations showed. This time, they checked everything from equipment malfunctions and data errors to other natural phenomena that could cause interference. The result: nothing was wrong. 14 independent telescopes around the world confirmed the same conclusion: the phenomenon was real, and the energy it released was real. If the cow had led scientists to believe LFBOTs marked the moment a star died, the Tasmanian Devil revealed another possibility. It could be the sign of a living compact object, a young black hole or magnetar, accreting material from the surrounding debris. Each time it gathered enough energy, it would blast out an intense jet of light, go quiet, and then erupt again. In other words, the Tasmanian Devil might not be the explosion of a star, but the heartbeat of a newborn object, a cosmic infant, still learning to breathe, and each breath is an explosion that shakes an entire galaxy. This discovery forced a complete reevaluation of all previous hypotheses. If an LFBOT isn't just death, but also life, then the line between those two concepts in the cosmos has never been less clear. While the Tasmanian Devil kept scientists busy searching for answers, the universe delivered a new shock, more powerful, stranger, and almost impossible to accept. On April 10, 2023, another blue flash erupted in telescope data. It had all the familiar hallmarks: enormous brightness, an extremely rapid explosion, and the characteristic spectrum of an LFBOT. But when the observation team used the Hubble Space Telescope to pinpoint its location, they discovered something unbelievable. The explosion wasn't in any galaxy at all. The event was named AT2023FHN, or the Finch. The name sounds gentle, but it sent shockwaves through the entire astronomical community. The Finch was located in the empty void of intergalactic space, 15,000 light-years from the nearest galaxy and over 3 billion light-years from Earth. In other words, it exploded in the middle of nowhere, a place where no stars should form and where nothing should be dying. This went against every existing theory. If LFBOTs are the collapse of massive stars, this was impossible. Those stars only live for a few million years, not nearly long enough to drift tens of thousands of light years away from their host galaxy before dying. The Finch didn't just break the theory, it shattered the logical foundation of the entire core collapse supernova model. From this, new hypotheses began to emerge. The first, the Finch was a star torn apart by an intermediate mass black hole, a theoretical type of black hole with a mass of a few hundred to a few thousand suns. When a star gets too close, the black hole's immense gravity would stretch and shred it into a stream of material, creating a violent and brief flash of light, exactly what was observed. This could also explain its remote location, as these black holes are thought to exist in faint globular clusters on the outskirts of galaxies. The second hypothesis, it was a collision between two neutron stars, an event known as a kilonova. These two stellar remnants could have been kicked out of their galaxy billions of years ago, wandering through space until they finally met. Their merger would create a powerful, brilliant, and extremely rare explosion, one that could perfectly mimic the signal of an LFBOT. Unfortunately, at the time, the Finch erupted. The LIGO Gravitational Wave Observatory, the only instrument capable of detecting the unique signal of a kilonova, was down for maintenance. With no gravitational wave data and no detected gamma-ray burst, both hypotheses were equally likely or equally wrong. Both scenarios are plausible enough to remain in the debate, but they leave behind a bigger question: if explosions like the Cow happen inside star-forming galaxies, while the Finch detonates in empty space. Then what exactly is an LFBOT? Is it a single phenomenon, or a collection of different explosions that just happen to share the same optical fingerprint? Perhaps LFBOT isn't a specific type of event, but a family of phenomena where the universe demonstrates many different physical mechanisms, all of which produce the same unique result: a blue flash that appears and vanishes before we have a chance to understand it. The Finch has forced every model back to the drawing board, and it reminds us of a simple truth in the cosmos. An exception isn't a mistake, it's nature's way of expanding the limits of our understanding. Today, astronomers are preparing for a new era of observation. The James Webb Space Telescope will search for faint globular clusters around the location of the Finch to see if an intermediate mass black hole is hiding there. On the ground, the Vera C. Rubin Observatory in Chile is preparing to come online, a machine that can scan the entire southern sky every few nights. With 10 times the sensitivity of the previous generation, Rubin won't just find individual LFBOTs, but hundreds, maybe even thousands of them every year. And with that, we will finally have what science needs most: a statistical sample large enough to separate order from chaos. In the next 5 years, scientists will focus on rapid response, capturing the full spectrum of data before the light disappears. In the next 10 years, with Rubin, we will have a population map, distinct groups of LFBOTs with different behaviors, each representing a unique physical mechanism. And in the next 20 years, we might, for the first time, identify their true origins, whether they are the newborn hearts of stars, hungry intermediate mass black holes, or colossal collisions between two stellar remnants. When that day comes, those fleeting blue flashes will no longer be a mystery, but a language of the cosmos, a language of birth, of energy, and of time. Because whether we can explain it or not, every time the sky flashes blue, it reminds us the universe is still alive, it is still telling its story, and we are still here to listen. If you too are amazed by these fleeting moments of the cosmos, stay with us. There are so many more stories waiting to be told, from dying stars to worlds yet unseen. Because the next time the universe blinks, you might just be the first one to see it.